Sound is a pressure wave. Pressure at any given region is quite easy to measure. In fact, a microphone does it all the time. Our ears are receptive to changes in pressure, and this tiny modulation of air pressure next to our ear is what is translated as sound. So pressure is as good a place as any to start our discussion on loudness. What is pressure then? You can think of it as a force that is responsible for displacing the molecules of air in a cross-sectional area of space. You've got to remember that this isn't wind we're talking about here. There's no movement of a mass of particles with sound. Sound is just a localized fluctuation or disturbance of the pressure of a fluid, like air. And this disturbance is propagated at the speed of sound, outwards in all directions. Going by this definition, there's a need for the pressure of the medium to exist already before sound can propagate through it. What is that? It's the pressure exerted by the air around you. The glorious atmosphere of the Earth, a whole 100 kilometers of voluminous air pushing down against us and the Earth's surface constantly without a break, with a force of about 101,325 Newton against each square meter measured at sea level. We can also say that the atmosphere exerts a pressure of 101,325 Pascal on us. Pascal being the SI unit or the standard unit of measure of pressure. 101,000 Pascal. Is that a lot? Doesn't seem like it. We don't feel constantly pressured by the atmosphere. That's because we've evolved to withstand this constant atmospheric pressure that virtually hasn't changed much over the course of history. This predictable atmosphere that we live under has helped develop unique adaptations in the human body, especially the ear, which is capable of perceiving even the slightest changes in pressure, several orders of magnitude lower than the equilibrium. And we'll find out soon enough that we cannot tolerate even relatively small changes of pressure in a short duration of time. Instead of talking about sound pressure waves on their own, we can think about them as being superimposed on top of the constant and static atmospheric pressure, oscillating around the equilibrium. A typical question you could ask now is, what's the pressure values of sound we normally hear? A normal conversation with a friend, observed from a distance of about 1 meter, is about 2 millipascal. The key point to note here is the distance from this source plays a very important role in determining pressure. If you're right up against the source, it's perceived louder since pressure is higher, as opposed to say 10 meters away. The relationship between pressure and distance is given by the inverse distance law, which states that the pressure is inversely proportional to the distance from the source. So as you move away from the source, the pressure decreases linearly. The second point to note is how low the pressure value is when compared to the atmospheric pressure. We can go much lower though. A calm room with the air conditioning on would be around 600 micropascal. The sound of your own breathing is as low as 60 micropascal. The lowest audible sound that a good pair of undamaged ears can hear is well established to be around 20 micropascal for a 1 Hz pure sine tone played right next to our ears. For a limited range of higher frequencies, we can actually hear sounds at a much lower pressure than this, but that's a topic for another day, and we'll sound that horn when we get to loudness perception. But for a majority of us, we can't perceive sounds this low. It's not because our ears are incapable of it, but just because we're surrounded by ambient noise from everywhere, which drowns out everything lower in pressure. Pause this video for a bit and try to listen to your own natural breathing without forcing it. Unless you're in an extremely quiet environment, you can't. You probably would have heard your own breathing in the dead of the night when you're in bed, but during the day, you're bombarded with ambient noise from the cooling fan of your laptop, the temperature control unit in your home, wind noise outside, or traffic noise at a distance. These sources of sound combined together make up a noise floor. Any source of sound with its pressure component below the noise floor is imperceptible to our ears. Its effects are masked and it's never heard. Naturally, the measurements made for the threshold of hearing of 20 micropascal is made in a controlled environment, in rooms that are designed to be completely soundproof from the outside and non-reflective from the inside, called anechoic chambers. If 20 micropascal is the threshold of human hearing, let's see what's on the other end of the spectrum. The sound of traffic on a busy roadway 10 meters away registers at around 0.2 Pascal. The sound of a jackhammer on a construction site a meter away is around 2 Pascal. We're already past the point where loudness isn't just an annoyance anymore, it's downright dangerous for prolonged periods of exposure. You remember the vuvuzelas? These demonic little devices used in unison in sporting events? They register at around 20 Pascal at a meter away. Imagine the loudest scream you've ever heard. Now imagine that an inch away from your ears. That's around 100 Pascal. And we've reached what's known as the threshold of pain, where the stimulus of sound starts to result in a perception that is physically painful. At these levels, even short bursts of exposure could result in hearing damage and even permanent hearing loss. Discussing anything about this is not incredibly useful for sound engineers, but it is interesting to find out what happens as we approach the atmospheric pressure. As the pressure mounts up, sustaining a pressure disturbance requires an immense amount of energy. But short instantaneous bursts of pressure variance are easy enough to create. For example, popping a balloon right next to your ear could result in a staggering 1000 Pascal of pressure disturbance. So never try that at home. As the pressure difference increases, the compression phase of the pressure waves start to build up in temperature, and this temperature gradient follows along with the wave. The heat is not transferred to the fluid, since the sound waves are adiabatic in nature, and there just isn't enough time for heat transfer to take place. The loudest sustained sound that's physically possible is a mean deviation of the atmospheric pressure itself, of 101,325 Pascal at sea level, at which point the wave swings from near vacuum to 2 atmospheres of pressure. Beyond this, the pressure wave is no longer a sound wave, but rather a shock wave. That's because the rarefactions of sound waves cannot be lower in pressure than vacuum itself, and the extra energy in the system distorts the wave violently and creates a non-linear wave where you have extra buildup of compression pressure. These waves are quite dangerous and violent, as they carry a pressure front which is incredibly hot and high in pressure, followed by an immediate drop in pressure and a suction pull towards the source. Well, that was a bit of trivia, but let's not get bogged down by what high explosives are capable of generating. Let's instead talk about what our instruments and devices are capable of producing. For all audio-related measurements, the range can be limited from the threshold of human hearing, which is about 20 micropascal, to the threshold of pain, which is around 100 Pascal. That's an order of magnitude around 6 times higher, and therein lies the problem. Representing this vast range of pressure values on a linear scale can get cumbersome, and you lose a lot of resolution at low pressure values. In the next video, we'll look at how a logarithmic scale is better suited to represent the range of data, and more specifically, the decibel scale used for measuring the sound pressure level.